Hi friends, I'm now taking you into a journey of integration, and I'll begin from somewhere here. So in this lecture, I would like to introduce you to the principles of the definite integral. Let us not forget that we are trying to study the double and triple integrals in all seriousness, and it's appropriate to begin with the definite integral of a single variable function. So this is the starting point, and then we'll slowly build up, and then we'll get into the business of double and triple integrals. Now, how do you represent a definite integral? How does it look like? So typically we have a function f of x, and then there are limits a and b within which we integrate. So integral a to b f of x dx is how a definite integral appears. A is called the lower limit and b is called the upper limit. So this is a visualization of the double integral. F of x, y is equal to f of x stands for the curve under which we are trying to integrate. And one visualization that directly comes to our mind is that definite integral yields an area. So we have the function f of x, and then on the x-axis we have the interval ab, and then the shaded portion is what we are trying to estimate. So this is only one of the interpretations of the definite integral. Now what you are seeing now here is what we call an improper integral, about which I'll be talking a bit later. But one can immediately recognize an improper integral by looking at the upper limit, which is infinity, and the shaded portion is having a lower limit 0 on the x-axis and going to a maximum of infinity. And if we can integrate that function and apply those limits, we get what is called the area under that curve. Now this is another very typical graphic, where again the function f of x, in this case 1 by x square, is an improper integral. I'll tell you why it's an improper integral again. There is something called a singularity at x is equal to 0. Singularity is a point where the function is not defined. So we can see that graphically also the two branches of the curve are not meeting at x is equal to 0. That makes x is equal to 0 a singular point. We'll come to these details later on, but I'm just trying to explain to you how definite integral in one variable appears like. So broadly, what we are seeing in this screen is the concept of area as a definite integral. Now, where do we encounter definite integrals? So I've given you some, I'm going to show you some slightly typical situations. Some of them can be easily interpreted, but let us see what is there. So in the first case, we have a concept of area once again, but here I would like to explain to you that this particular curve is sometimes above the x-axis, once it goes down below the x-axis, and again it goes above the x-axis. So this is what is known as the signed area, where we have positive areas whenever the curve is above the x-axis and negative area when it goes below. So this can be one situation where we can think of areas as an application of the definite integral. Then this is an example from economics, where we talk about how to estimate the equilibrium point given the demand function, and So we will not get into the jargon of economics now, but once again, it is what we call the area under the demand function. So it comes everywhere practically. So we have seen a geometrical situation in A, an economic model in B, and then this is an excellent example of how to use a definite integral for finding out the volume of a solid of revolution. And you can see those disks, circular disks, which form part of the solid. We'll come to that concept later on. So what we have on the screen right now is an area example, and then we've got an economic model. Then we've got a geometrical application for finding the volume of the solid of revolution. And then this is another application of integration that deals with finding out the exact length of the arc of the curve. So where you can see delta S is actually the length of the small element of the curve. And when we actually develop the mathematical model for the arc length, we approximate that small arc length by a straight line so that we can use the Pythagoras theorem and then develop a model. Let us not get into the details, but I'm just telling you that this is another very important area where definite integral is seen to estimate the arc length of a curve. Then I'm showing you one more. This is a very typical example where we've got a closed curve, but look at the shape, whether we can do calculations like finding its perimeter or the enclosed area, whether integration will come to our aid is a very big question here. Normally, it's very difficult to apply definite integrals to situations like this. I will not go into the depths of how to handle it, but probably this is an area where it's not so easy to apply the definite integral. So there are 4 situations where you can apply and one a little bit doubtful. Now, where does the definite integral arise from? So there is something called the fundamental theorem of calculus, about which I had explained earlier. So when we say f of x is integrable, I mean I'm searching for a function g of x whose derivative matches the function f. That means g dash is equal to f. If you can find that g such that g dash is equal to f, that means you can integrate the function. This is what the fundamental theorem of calculus says. If you're able to integrate, then the job is done. You integrate f of x from a to b, and then the output is g of x, then apply the limits a to b. Obviously, you know that the upper limit first gets substituted, then the lower limit gets substituted, then you take the difference. And you must consider yourself very lucky if you are able to get g of x by the integration of f of x. In higher mathematics, we cannot always guarantee that it is always easy to find the integral of f of x. But if you can do it, that means the fundamental theorem of calculus is in action. Now, these are some of the very important principles that one has to use, because for fast computation, sometimes directly integrating f of x may not be possible. So you can always depend upon this property. Whenever f of x is not amenable to direct integration, you can try integrating f of a minus x, which means the area under f of x and the area under f of a minus x within the same limits are the same. So this is a valuable property, but there are some specific situations where it is used. This is a slightly advanced property where the limits are now 0 to 2a. Now 2a is just a way to express the property. For example, 0 to pi may have to be visualized as 0 to 2 times pi by 2 and so on. So 0 to 2a f of x dx can give 2 types of outputs. One output is directly 0, for which f of 2a minus x is equal to minus f of x. The second possibility is 0 to 2a f of x dx becomes 2 times 0 to a f of x dx when f of 2a minus x is equal to f of x. This is considered a slightly higher property than the first. Then this one is another very valuable function where the nature of the function f of x will decide whether the output will be 0 or 2 times 0 to a f of x dx. Observe the left hand side, the limits are minus a to a f of x dx. So there are something called odd and even functions. An odd function is a function that is symmetric about the origin, and an even function is a function that is symmetric about the y-axis. So you study the geometry of f of x, and then you see whether it's an odd function or an even function. And once it is decided it's odd or even, you can use this property. These properties will vastly simplify our calculation of the differential. Now what you are going to see in the next couple of slides are specific integrations of the sine and cosine functions. So 0 to pi by 2 sine theta power m or 0 to pi by 2 cos theta power m both produce identical results. Remember, the range should be 0 to pi by 2. So what you do is you begin with one number less than the power m in the numerator, m minus 1. You begin from there. Suppose m is 5, so you start from 4. And if you can observe the progression, m minus 1, m minus 3, m minus 5, etc. means you drop 2 values each time. And how far should we go till you don't land into a 0 or a negative number? When it comes to the denominator, you start with the m itself, and then again there's a gradual decrease of 2 numbers, again as long as you don't land into zeros and negative numbers. And observe carefully, when m is an even positive integer, you will have to further multiply your answer with pi by 2, and when it's an odd positive integer, you just don't have to do anything, or you multiply with 1. So this is a very valuable property, but the limits must be 0 to pi by 2. The fourth one is a special property for sine functions when the limits are 0 to pi. So any time you have a sine theta power m from 0 to pi, you can write it as 2 times 0 to pi by 2 sine power m. Whether it's an odd positive or even positive or any real number, it works. Whereas when it comes to the cos theta power m function from 0 to pi, there are 2 cases. The output will be 0 when m is an odd positive integer, and the output will be 2 times 0 to pi by 2 cos theta power m when m is an even positive integer. So these are all very intricate and a little bit confusing initially, but with constant practice you can remember these results. But these are all highly applicable. Now continuing the sequence of results, then we go to 0 to 2 pi cases. So 0 to 2 pi sine theta power m and 0 to 2 pi cos theta power m give similar results. It breaks down into 2 cases again. The output will be a 0 when m is an odd positive integer, whether you deal with a power of sine or a power of cos. And the output will be 4 times 0 to pi by 2 sine theta power m when m is an even positive integer. Once it is reduced to 0 to pi by 2 situation, the previous results can be adopted. But then if you look at the 8th one, where we have sine theta power m and cos theta power n coming as a product from 0 to 2 pi, there are 2 cases. The output will be 0 when either m or n or both of them are odd positive integers. And when both of them are even positive integers, the output will be 4 times 0 to pi by 2 sine theta power m and cos theta power n. So these are all the direct principles. Do we have any special techniques to evaluate integrals? Yes, we have to master these things. Integration by substitution in a general way, integration using trigonometric functions, which will lead to the previous principles that I just now introduced. Integration by parts, this is what we call as a product rule of integration. Integration by successive reduction, and integration by invoking special functions, which generally is seen in engineering applications. Now, these are some of the special tools of integrating using the so-called special functions, beta and gamma functions. So if you look at each one of them, they are highly contrasting. If you look at the first one, 0 to infinity e power minus x, x to the power of n minus 1 dx, the output will be a gamma n, which is a number. Gamma n is a symbolic representation of the answer. So gamma n is, which is written as 0 to infinity e power minus x, x power n minus 1 dx, can be remembered as a gamma integral also. And this gamma n has got some properties which I'll be sharing in my next screen. But there are some integrals of the form x power m minus 1 into 1 minus x power n minus 1 dx from 0 to 1. And this output will be a number which is represented as beta m comma n. And this beta is a special function. So the problem is, unless you know what are the gamma n values and the beta mn values, you cannot produce a numerical result. We will talk about that in a couple of minutes. Then if you look at the third result, 0 to pi by 2 sine power m theta cos power n theta d theta can be expressed as a beta function, half beta m plus 1 by 2 n plus 1 by 2. And once it has been converted into a beta function, then it is always possible to evaluate it. I will tell you how. Then there are two more typical integrations that once in a way crop up. 0 to infinity x power m minus 1 by 1 plus x power m plus n dx. And 0 to infinity x power n minus 1 into 1 plus x divided by 1 plus x power m plus n dx. Both of them giving the beta function with parameters m and n. Okay, the integrals are identified and how to convert it into a gamma or a beta function are understood from this. How do I evaluate my answers? This is where you require these properties. Gamma half is root pi. It comes through a slightly solid derivation, but we are only compiling results in this presentation. Then gamma k into gamma 1 minus k is pi by sine k pi whenever k lies between 0 to 1. Then gamma n plus 1 can be reduced as n into gamma n, and you can use it for positive fractions. Q plus stands for positive fractions. The same result can be manipulated as gamma n is equal to gamma n plus 1 by n whenever n is a negative fraction. And the last one is a very valuable thing. All beta functions can be converted into a gamma function. Beta m comma n is equal to gamma m into gamma n to gamma n plus n. So it's not that easy. Some of them are easily understandable, but to integrate using special functions like gamma and beta requires a lot of practice. This is again a very, very valuable table that can be used whenever you are integrating functions. And you can see in this table, for a given function, what is the substitution that we must adopt. For 1 minus x squared, x is equal to sine theta is a natural substitution, because when you look at the trigonometry there, 1 minus sine square theta becomes cos square theta. So it gets simplified. Like that, a square minus x square requires x is equal to a sine theta. That's a natural substitution. And when you take 1 minus x, we have x is equal to sine square theta. And I hope you are now beginning to understand why these substitutions are so easy to accept. Okay. When it comes to the 5th, 6th, 7th, and 8th, the tan function will be the choice. 1 plus x squared, take x is equal to tan theta, because 1 plus tan square theta becomes secant square theta. So that's a vast reduction in the size of the function. When you have a square plus x squared, use x is equal to a tan theta. When you have 1 plus x, take x is equal to tan square theta. And when you have a plus x, you take x is equal to a tan square. Of course, it will be appropriate to have a quick exercise on all that I presented today. So what we are going to see in a sequence of this particular presentation is some problems, because unless you get hold of the definite integral of a single variable function, you will not be able to touch the double integration and triple integration area, because double and triple integrations are called iterated integrals. That means you integrate one after the other. Each one is a definite integral. So if your fundamentals of definite integration are not strong, then you may end up not performing double and triple integration. So I'm going to take up some simple problems on indefinite integration. That means integration without limits. Then how to choose a substitution, how to recognize a substitution is required. A couple of problems on integration by parts. Then slightly advanced integration by successive reduction. And then I'll give you a couple of problems on the definite integral, all that I presented today. And that also includes the beta and gamma functions. And then I may show you a couple of very simple applications of the definite integral, like a couple of area problems and a problem on economic models. So dear friends, let us await a live session on problem solving. But meanwhile, I expect you have a quick review of all these things. Thank you.